The next topic in the applications of definite integrals chapter is the washer method. And the washer method is used to find the volume of the solid that's generated when you're rotating several equations around the x or y axes. In this first example, I need to find the volume of the solid generated when that region is being rotated around the x-axis here. And a very good sign where you know when to use the washer method is when the problem gives you two equations. So when you're given two equations, you should definitely be thinking about using the washer method. Now from class, there is a simple formula for the washer method, and that is volume equals to pi. And I call it the big radius squared minus the little radius squared, and then I'll multiply that by the height. So that's the general formula for the washer method. It's very similar to finding the volume of a cylinder with a hole in the middle. And to kind of finish this kind of formula off, you would actually integrate this from a to b. Okay, so let's keep this formula in mind when we're doing some of these washer method questions. Okay, so for this very first problem, let me just kind of erase this formula here, and I would go ahead and actually graph these two functions. So if I have y equals to root x, that looks like this. That's going to be y equals to root x. And then I have y equals to 1/2 x, so that's going to look like, actually, let me just kind of redraw my graphs here. This is y equals to root x. And y equals to 1/2 x, that's going to look like that. So that's y equals to 1/2 x. After you graph your two equations, I would go ahead and find the intersection points. So over here, the graphs do intersect at 0, 0. Then after that, I will at least find the x-coordinate where the two graphs intersect, and you can do that by letting the two equations be equal to each other. So that's going to be root x equals to 1/2 x. After that, you can square both sides. And after that, I would get x equals to 1/4 x squared. Then I'll bring the x to the other side. So that's going to be 0 equals to 1/4 x squared minus x. From there, I can factor out an x, and I would get 1/4 x minus 1, and that equals to 0. From here, I know that x equals to 0 there, and that kind of matches up with the origin there. And for this one here, I get 1/4 x equals to 1, and then x equals to 4. So basically, the graphs intersect when x equals to 4. Okay, so going back to my graph here, I know that this is, sorry, let me just erase that. I know that this x value here is 4. Okay, so in the problems, usually the problem will say the region enclosed, that region is being rotated around the x-axis. The region that the problem is referring to is the area between the two curves, all right? So this is the area that's, or the region that's enclosed between those two curves. So let me just erase all this, and I'll erase all that now. So this is the region enclosed by those two curves. Okay, now that region right there, that's going to be rotated around the x-axis. So this is the x-axis, it's going to be rotated around that axis right there. So what I'm going to do right now is I'm just going to show a few more visual pictures of what that would look like, and then we're going to actually solve the problem. Okay, so if I go down here, here are a few more visuals of what's happening in this particular problem. You know, this one right here, I think we established that as y equals to root x. And the bottom graph is y equals to 1/2 x. And then if I'm going to just maybe shade in this red region here. This region right here is being rotated around the x-axis. And if I take a look at this very first diagram, I'll use green this time, but this is the area that's being enclosed. So that green area is being rotated around the x-axis, and if that happens, you get another shape that's symmetric just below the x-axis like this. And then inside this cone, there's a cone that's being shaped, but inside that cone you get these washers now that have a hole in the middle. So as you can see, there seems to be a gap between the two graphs that creates this hole, and that's why we call it a washer. And in this next diagram right here, I think the washer is very easy to see. It's this thing in green here. That's a washer right there. And there's going to be infinitely many washers inside that cone. And here's a top view of what's happening inside the cone. There's my washer right here. And basically, in order to calculate the volume of one washer, and then we can integrate that to find the volume of the entire cone there, we're going to have to look at the outside radius. So if I use my green marker here, there's my outside radius here. And then we also need to look at the inner radius, which is this purple line right there. So if you take a look at those two dots, just erase that again. This green dot is the outer function, and this purple dot is the inner function. So based on those two radii, we need to set up our volume equation here. Okay, so let's go back to the first diagram here. The best way to do a problem like this is, okay, let me just kind of set up the original, let me just set up a volume equation for one washer. So that's going to be r squared minus little r squared times height. Now, since we're rotating around the x-axis, that means my height is going to be dx. Just like the disk method, if you're rotating around the x-axis, the height is always dx, and if you're rotating around the y-axis, then your height is dy. So that's step number one. Substitute dx for your height. And then what you need to do now is you got to find your outer radius and your inner radius, or your outer function and your inner function. And that comes from looking at your graph here. I think this graph right here is probably the easiest to find the outer and inner functions. What I like to do is I just draw a straight vertical line between the area, and this dot right here, that represents the big R, and the little dot down there represents the little r. Okay, so let me just kind of repeat that, and let me just draw let me draw two arrows this time. So that black dot right there is the big R, and the green line is going to be the little r. All right, so it's kind of like top minus bottom. So the top function is this guy right here, which is root x, and the bottom function is going to be this line, which is 1/2 x. Okay, so if I had to kind of put that together here, the bottom function is that guy, and the upper function is this guy. Okay, so let's go ahead and plug those expressions into our equation here. So that's going to be pi times, once again, my upper function is root x, so it's going to be root x squared, so that's going to be root x minus 1/2 x, and all that's being squared. So that's the volume for one of the washers, and if I want the entire region, so if I want to stack up washers and actually fill this entire cone here, basically I need to integrate all the way from, well, let's go back to the original problem. I need to integrate from x equals 0 all the way to 4. Okay, so if I go ahead and establish my boundaries here, I'm going all the way from 0 to 4. And that right there is my expression to find the volume of the washer. And before you find the antiderivative, let's go ahead and simplify the inside here. So root x all to the power 2 is simply going to be x minus, and then 1/2 x to the power 2 is going to be 1/4x squared. And then I can close the bracket and then multiply by dx. Now we're ready to take the antiderivative here. So the antiderivative of x is x squared divided by 2 minus 1/4, and then the antiderivative of x squared is going to be x cubed divided by 3. And then that's going all the way from 0 to 4. And then there's a pi in front. If you want, you can take the 1/4 and the 1/3 down there, and you can multiply the denominators there. So 4 times 3 is going to be 12. So I can just erase that, and I can put a 1/12 in front. Okay, let's go ahead and use the fundamental theorem of calculus. So the upper bound goes first. And the good news is we have a 0 for the lower bound, so that means I don't need to evaluate the lower bound because everything goes to 0. Okay, so if I put in 4, that's going to be 4 to the power of 2 divided by 2 minus 1 over 12. And then we have 4 being raised to the power of 3. And then I can close the bracket there. And let's go ahead and finish off this calculation here. There's a pi there. 4 to the power of 2 is going to be 16. So 16 divided by 2. And then minus. And then 4 to the power of 3 is going to be 64. And then I can divide that by 12. After that, that's going to be, let's continue the calculations here. So I have a pi. 16 divided by 2 is going to be 8, minus, this will be 16 over 3, I believe. And then that should give me 8 pi divided by 3. Okay, so that's it for that particular problem. Let's move on to question number 2. For question number 2, I need to find the volume of the solid rate generated when the region enclosed by the following curves is revolved around the x-axis. So I have two functions, 1 and 2. So that's a good sign that I need to use the washer method. Before I use the washer method, let's go ahead and just graph the two functions to see what area is being rotated. So if I take a look at y equals to x squared, that's just a simple parabola. And then if I take a look at my next equation here, if I isolate for y, that's going to be y equals to the square root of 8x. And that's going to look like this. There's y equals to root 8x. And this is y equals to x squared. Okay, so this region in between, that red region right there, that's going to be rotated around the x-axis. And then some kind of solid is going to be formed, and then we have to use the washer method to calculate the volume of that object. Before we actually get into the formula and a few more visual diagrams, let's go ahead and find the intersection points. So for this particular problem, the graphs do intersect at the origin, which is 0, 0, and then we've got to find out where they intersect over here, right? All right, so in order to do that, let's make the equations equal to each other. So x squared equals to root 8x. After that, I can square both sides. If I square both sides, I get x to the power of 4 on the left-hand side and just 8x on the right-hand side. And then I can bring the 8x to the left-hand side, so it will be negative 8x equals to 0. And then from there, I would go ahead and factor out one of the x's, so that would be x cubed minus 8 equals to 0. And then this x would be x equals to 0, which is the 0 at the origin there. And then if I set that equal to 0, that's going to be x cubed equals to 8, and x would equal to 2. Okay, so x equals to 2, let's go ahead and just label that in my diagram. That's going to be very important when I set up my, my integral expression. So this x value here is going to be 2. And if you want to go ahead and find the y value, you can. So 2 to the power 2 is going to be 4, so the y value there would be 4. Okay, let's go ahead and look at a few more visual diagrams before we set up our equation for the washer method here. Okay, so here's the first diagram that I had. Once again, we're taking this red region right here, and we're going to be rotating that around the x-axis. Just a reminder that the bottom function is y equals to x squared, and the top function here is going to be y equals to root 8x. Okay, so let's focus on this red region right here, and let's just see what's going to happen when I rotate that region or that area enclosed around the x-axis. So here's a 3D diagram right here. This is the region right here that's being rotated around the x-axis, so around here. And as you can see, I do have the other part of that region just below the x-axis here. It's very symmetric, so it looks like we have a cone there, and I'm not sure if you can really see it from this angle or not, but you're going to have all of these washers with a hole in the middle, and they're going to be stacked up. Here's a little diagram with the hole. So if you take a look at this region right here, the red region, the green region, the blue region, there's a gap in there creating a hole. And here's a side view of what the washer will look like. So here's the washer, And then here's that hole that I'm talking about right in the middle. Okay, and then here's kind of a top view looking down inside the washer. And our goal is if this is my center right here in green, I need to go all the way to the outer function. And then with this red dot, with this red line here, I need to go all the way to the inner function. So I need to find those two functions in order to set up the washer equation here. The best diagram to look at when you're setting up the washer method is usually the first diagram right here. Let me just erase this. So I think everyone can agree that this is the this yellow part represents the area between those two curves, and I would just draw, you know, a line from the axes all the way to the top function. That's your big R, and your little r is a line from the axes all the way to the inner function, which is your little r. All right, and remember the little r had the equation of the equations were y equals to x squared for the parabola, and for this top function here, the equation was y equals to root 8x. So we're going to be using those two equations to set up our washer equation here. Okay, so here's step number 1 for the washer equation. Let's just go ahead and write out the volume for one of the washers. And since we're rotating this around the x-axis, that means your h has to be dx. And then if I take a look at my big R here, that's pretty much going to be this function right here, and that represents root 8x. And my little function is going to be that part right there, which represents x squared. So I just insert those two functions into my volume equation here. So if I do that correctly, I have pi, and then that's going to be root 8x, and then squared, and then minus the parabola, which is x squared, and that's also being squared, and then times by dx. Times by dx. And let's go ahead and put our integral sign here. If I go back to the original problem here, we're going all the way from 0 to 2. So those are my x values, 0 to 2. So let's go ahead and plug a 0 here and a 2 there, and there is my volume expression here for the washer. And I just need to evaluate this now. If I raise all this to the power of 2, that's going to be 8x minus, and this part right here raised to the power of 2 is going to be x to the power of 4. And then I'm going from the integral from 0 to 2, and then there's a pi in front. So we just got to simplify the inner brackets, and then we can take the antiderivative from here. Okay, so the antiderivative of 8x is going to be 8x to the power of 2 divided by 2 minus, and then the antiderivative of x to the power of 4 is x to the power of 5 divided by 5. And then I'm going all the way from 0 to 2, and then there's a pi in front. What's really nice is there's a 0 on the lower bound there, so we don't need to really do much with the lower bound. We can just focus our attention on the upper bound by plugging 2 in for the x's. Okay, if I do that, I get pi, and then I get 8 times 2 squared divided by 2 minus 2 to the power of 5 divided by 5, and then I can close that bracket off. And then from here it's just doing the calculations here, so that's going to be pi. This part right here, 2 to the power of 2 is 4. 4 divided by 2 is 2, and 2 times 8 is going to be 16. So that's going to be 16 minus 32 divided by 5. And then if you keep on simplifying that, that should be 48 pi divided by 5. And that's your final answer for that particular question. Okay, let's keep on moving along here. There's quite a bit of washer questions to complete here. Okay, here's my next washer question here. I know it's a washer question because there's two equations, and this is being rotated around the x-axis, and once again I just need to find the volume of the solid generated when that region is being rotated around the x-axis. Okay, let's start off by graphing the two functions because I need to find the intersection points. So here's a parabola, y equals to x squared. So there it is, y equals to x squared. And then I also have a linear line with a y-intercept of 2. So there's my linear line just like that. Okay, so that's going to be y would equal to x plus 2 in green. Okay, let's go ahead and find the two intersection points. The two intersection points, they kind of help me with the boundaries for my when I'm integrating. And then after that, this area between the two curves, that purple region there, that's going to be rotated around the x-axis. And then we'll have a few more visuals to see what that looks like. But let's go ahead and find those two intersection points first. In order to do that, we got to make the two equations, x squared equal to the linear line, which is x plus 2. If I bring x plus 2 to the other side, I get negative x minus 2 equals to 0. And then I can factor the left-hand side here. All right, so if I factor that, that's going to be x minus 2 and x plus 1. And if I set those equal to 0, x should be 2 and negative 1. Okay, so if I use a little bit of logic here, this is probably going to be 2, and that's going to be negative 1. So those are the two x values where I will be setting up my integral expression later on in the washer equation. Okay, let's take a look at a few more visuals now. Here's that region again. And remember, this is going to be 2, and this part here is going to be a negative 1. Okay, so if that blue region is rotated around the x-axis, let's take a look at a different view here. This is kind of looking at the view from the top, and I'm not sure if you can see this purple region here. That purple region is the part that's being rotated around the x-axis, and if you do that, you might see this washer that's being formed, which is, I'm trying to highlight in red here. Here's my washer. All right, so we're going to have many of these washers as I go from left to right. And if we can find the volume of one of those washers, we can find the volume of everything by integrating. Okay, so as those two graphs are being rotated around the x-axis, here's another side view of what's going on here. Once again, if you look very carefully in the diagram, this region right here in black, that's the region between the line and the parabola. And you can see that just below it, there is, since there's symmetry in these problems, there is the other region that's being generated just below the x-axis. Okay, I'm just going to erase that, but that's what it looks like that's what it looks like from a side view. And here you can see the washer here in red. Actually, I should use a different color there, maybe a blue marker here. Actually, no, blue doesn't work either. Maybe green. So there's my washer right there on the side. So we're going to have lots of those washers being generated, and here's a kind of a side view from the top where my washer is being generated. And if you look closely, this is that region between the parabola and the linear line. So that area is still in there, it's just being rotated multiple times. And then here's a view from the top looking down into the cone, and once again, there's my washer there, and what I need to do here is from the center, we got to find the outer radius, and we also need to find the inner radius right there. Okay, so those are some visual diagrams of what this equation would look like, what the solid would look like once we rotate those two functions around the x-axis. Okay, let's go back to the original diagram here, this one right here, and let's go ahead and write an expression for our volume of the washer here. So volume equals to pi bracket r squared minus little r squared times height. Since I'm rotating this around the x-axis, that means my height has to be dx. So anytime you're rotating around the x-axis, the height is always dx. And then let's go ahead and find our outer function, which is our big radius, and then we'll go find our inner function, which is the little radius. Okay, so if I go back to the shader region here, I'll highlight this in yellow here. What you're really doing is you just draw a line from the axes all the way to the top function. That's your big R. Okay, so that means x plus 2, which represents this top part, that is the equation of big R. And then I take another point from the axis, and then I just go to the inner function, and that's my little r. So little r is going to represent the parabola, which is x squared. Okay, so the x squared will be there, and my linear line, x plus 2, is going to represent big R. All right, so let's go ahead and plug those in. So I have x plus 2 all being squared minus the parabola, which is just bracket x squared, and that's also being raised to the power 2, and then multiply that by dx, and then I have my pi in front, and I might as well just set up my integral now. This is why we need to find the two intersection points. The two intersection points are -1 and 2. So I'm going from -1 all the way to 2. So now I can just kind of insert that into my volume equation there. Before you find the antiderivative, it'd be best to kind of simplify the inside expressions here. So if I use FOIL here, that's going to be x squared plus 4x plus 4. And this is going to be minus x to the power 4. And then all that is going to be let's put that in a bracket there of the dx. And then I'm going all the way from -1 to 2, and then a pi in front. Okay, so I think now we're ready to find the antiderivative, and find the antiderivative of this expression will take a little bit of time. So that's going to be x cubed divided by 3 plus 4x squared divided by 2 plus 4x, and then minus x to the power of 5 divided by 5. And then we'll put our square brackets there, and we're going all the way from -1 to 2. Volume equals to pi times all that. I do want to say this is going to take quite a bit of work to evaluate this, because I do have numbers on my upper and lower bounds here. So if I had 0, then things would have been easier, but I actually have numbers for both my upper and lower bounds here. So I'll just show the substitution step, and then I'll just jump to the final answer there, just because I want to save a little bit of time here on the calculations. Okay, so that's going to be 2 to the power of 3 divided by 3 plus 4 bracket 2 to the power 2 divided by 2 plus 4 times 2 minus 2 to the power of 5 divided by 5. Okay, so do take a little bit of time to actually compute all of that, and then I'm going to take all that and I'm going to subtract another bracket here, this time with a -1. So -1 to the power of 3 divided by 3 plus 4 times -1. I always put my negative signs in brackets when I'm inserting. And then plus 4 times -1 minus -1 to the power of 5 divided by 5. And then I can close that bracket. And then I can also close another bigger bracket there. Okay, so unfortunately I don't want to use the rest of this video time to actually calculate the answer here step by step, but the final answer is 72 divided by 5 pi. Please take a little bit of time to make sure you can actually do the work on that, and that should be your final answer for that problem. Okay, let's move on to the next question. Okay, let's take a look at the next washer question here. Find the volume of the solid generated when the region closed by the following curves is revolved around the x-axis. Okay, so here's my function there. Let's go ahead and, since there's two functions, let's go ahead and sketch the graphs. Okay, just one sec. Okay, so this guy right here is half a circle, so kind of looks like this. It's half a circle. I mean, the full circle would be all the way around, but it's only half of it. And since there's a 25 there, I know that this is going to be -5, and this is going to be 5. So the radius of the circle is 5 because of this 25 there. And then we have a horizontal line of y equals to 3. So y equals to 3 looks like that. And there it is. Okay, so what I'm going to do next is I'm going to find the intersection points, these two green dots. And let's go find those intersection points first before I continue moving on with the setup of the washer method here. Okay, so if I want to find the intersection points, I take my equations, 25 minus x squared, and I make that equal to my horizontal line, which is 3. After that, I can square both sides. If I square both sides, I get 25 minus x squared equals to 9. And then I can bring everything to the right-hand side, so that's going to be x squared. Sorry, I'll bring the negative x squared to the other side. And then I'll take my 9 and I'll bring that to the other side. So that's going to be 25 minus 9. And 25 minus 9 is going to be 16. And then if I take the square root of both sides, if I take the square root, it's going to be plus or minus. So plus or minus 4 equals to x. Okay, so if I go back to my diagram here, this is going to be a negative 4, and that's going to be positive 4. And I know that this region right here in yellow, that's going to be rotated around the x-axis. Okay, I think what I'll do here is I will go ahead and just solve the problem here, because I don't think I need to jump into the visual diagrams right away to see what's going on, because for all these problems I can just draw a vertical line right through the shaded region, and I always know that the top function is going to be my big R and the bottom function is going to be my little r. Okay, so purple is the top function, big R, and the red dot is the little function, which is little r. So if I go ahead and write my volume of the washer here, it's going to be volume equals to big R squared minus little r squared times my height. Now, since I'm rotating around the x-axis, that means the height is going to be dx. Okay, and then I've already established that the purple dot right here represents the big R, and the equation of that top function is going to be 25 minus x squared. So this guy here is now going to become 25 minus x squared, and then there's a 2 there, so raise to the power 2, minus this red dot right here represents the bottom function, which is simply just this horizontal line. So that horizontal line represents the little r, so that's going to be 3 to the power of 2, and all that's going to be in a bracket there, times dx, and then volume equal to pi, and then I just integrate this from the two intersection points from -4 all the way to 4. Okay, so let me just start erase all this here. I'm just going to clean all this up if I can. Okay, so let me erase the -5 and the 5 there. There it is. So that right there is my expression right there for the washer equation. Now, let me go back to my diagram here. We haven't talked a lot about this in class, but if I look at this green region right here, because it's a circle, that green region is the same thing as this blue region. It's a circle, and if you cut the circle in half, it's completely symmetric. So what I'm planning to do here now is I'm going to actually just calculate the area from 0 to 4 and then double it. Okay, so I'm going to change my boundaries. Instead of going from -4 all the way to +4, I'm going to go from 0 to 4 and then double it. One of the reasons why I want to change this lower bound to a 0 is because that's going to make the calculations a lot easier. So I can change this to a 0 now, and then to modify that, I should have a 2 in front, in front now to double that, and that can save me a little bit of time when I'm doing my calculations. Okay, let's go ahead and simplify this. If I simplify that, that's going to be 25 minus x squared minus, and then 3 to the power 2 is going to be 9. And then if I combine the 25 and the -9, that's going to be 16. So 16 minus x squared. Let me just write that up here again. So 16 minus x squared. And then dx. And then this is going from the integral from 0 to 4 of 2 pi. All right, so I simplified as much as I possibly can, and now it's time to find the antiderivative here. So the antiderivative of 16 is going to be 16x minus, and then the antiderivative of x squared is going to be x cubed divided by 3, going all the way from 0 to 4, and then the 2 pi in front. All right, so if I apply the fundamental theorem of calculus here, I just insert the 4's now. So if I keep on going here, that's going to be 2 pi bracket 16 times 4 minus 4 to the power of 3 divided by 3. And if you do all the math there and figure this out, I believe that's going to be 256 pi divided by 3. Okay, so that's the numerical answer. Let's just go back to the visual diagram here. At the start, I didn't really go through any, let me just erase this here. Let me just kind of talk about this particular diagram in a little bit more detail here. Let me just get a very dark marker here and highlight this area here, this region here. And that's being rotated around the x-axis. And what I didn't do prior to doing all the calculations is providing some visual diagrams on what that would look like. So now I do want to take a little bit of time to provide some visual diagrams. So here's that region that's being rotated around the x-axis. I believe that's going to be 4, and that's going to be -4. And here's a top view of what's happening here. Here's the x-axis right there, and here's the region that's being rotated around the x-axis. And once that region is being rotated, you'll notice that we have this washer right here in red. That's one washer that's being formed. And within that region, that black region, there's going to be multiple of these, infinitely many of these washers being generated. So let me give you another side view here. This is kind of looking at the diagram at a different angle here, and if you look very closely, this region right here in black, that's the area between the two curves. So that's kind of a side view there, and there's my washer being generated. And if I keep on rotating this many times and stacking up all the washers, it would actually look like this. It's a very thick solid in there. It kind of looks like a ball with a hole in there. And if you look very closely inside, I mean, this is still the area that's being rotated around the x-axis. So that's the area between those two curves that's been rotated infinitely many times, creating this solid here. And then this is another side view of what's happening with this object. And if you look at the right-hand side here in black here, this is that region that's, I'm trying to highlight it right here. This is the region between those two graphs that's been rotated around the x-axis. And the x-axis is this black line right there. So this is really a different view of what's happening here. Usually when I started the problem, I think there was your axes, and I believe there was your line y equals to 3, and then it was something like that. And that was the region that was being rotated. So we're usually used to seeing like diagrams in this angle, but now it's being completely shifted sideways to give you an idea of what's happening on the inside when this region is being rotated around the axis here. So it definitely looks really weird, but we still, in order to solve it, we can just use the top minus bottom method. And all I did was I kind of drew a vertical line right there. There's my top function, and there's my bottom function, right? So that's y equals to 3, and that's the square root of 25 minus x squared. All right, so that's what the diagram looks like when you rotate it many times. Just there for some interest. Okay, after this, let's go over a few questions where we're rotating around the y-axis now. All right, this is the very first question where we need to find the volume of the solid generated when we're rotating around the y-axis. And since we have two equations, we're still using the washer method here. All right, so for the washer method, let's go ahead and graph these two functions. If I have this function here, y equals to root x, and then I have this linear line, which is 1/3 x, so I'm going to just graph it like that. That's y equals to 1/3 x. Okay, now remember, we're rotating around the y-axis this time, so we have to take a different approach when we're doing this. But this region enclosed, that yellow part is being rotated around the y-axis. Okay, let's go ahead and find the intersection points because I still need those. Whether you're rotating around the x or y-axis, finding the intersection points is important. All right, so in order to do that, let's just do a side calculation over here. So root x equals to 1/3 x, and then I'm going to square both sides. If I square both sides, I get an x here, and remember, I'm squaring all of that, so that's going to be 1/9 x squared. and then after that I can bring the x to the other side, and that's going to be 0 equals to 1 over 9x squared minus x. And then I can factor out the x's, and I get 1 over 9x minus 1 equals to 0. And if I set that equal to 0, that means x equals to 0. And this right here, that's 1 over 9x equals to 1. And x would equal to 9 because I'm timesing both sides by 9. Okay, let's go ahead and put that in our diagram here. So this point is going to be 0, 0. And this point right here is going to be 9. And if I want to find the corresponding y value, the square root of 9 is going to be 3. All right, so there's my intersection point at 9, 3 and at 0, 0. Okay, so let's take a look at some visual diagrams to see what's happening when we rotate this region around the y-axis now. Okay, so here's the same diagram right there, and we're rotating around the y-axis. Remember that was 9, and I believe that was 3. So actually, let me just maybe I'll just put the coordinates right at the intersection point. So this point is going to be 9, 3, and that point right there is going to be 0, 0, and that yellow region is being rotated around the y-axis. So here's another view of what happens when we're rotating around the y-axis here. And if I had to kind of label my diagram here, I believe this point right here is going to be 9, 3. And then if I rotate this around the y-axis, I don't think I have the right scale here. Just ignore the numbers on the scale here. But this point should be -9, 3, just to be symmetric. And at the very bottom here, that point is 0, 0. So I'm sure you can see this blue region right here. Actually, that blue doesn't come out very nice. Let me just use a green marker here. This green region right here, that was the area between the two curves. And if I rotate around the y-axis, you get this symmetrical area right there. And what's happening in the middle is that you're getting these washers that are being formed. Okay, and these washers are of different size. And obviously at the very top, the washers are a little bit bigger. So all these washers are going to be stacked vertically until that cone is full, and there's going to be a hole in the middle. Here's another visual diagram, kind of from the top-bottom view, and this is what it looks like from the top-bottom exactly. And here's that washer that we've been focusing on for this entire lesson here. And in order to set the washer method, I mean, from the center, we're going all the way to the very end for the big R, and we're also going to the inner function to find the little r. Okay, so let's go ahead and set up our washer equation now that we have a visual understanding of what this shape looks like. Okay, so when you're doing these washer questions, when you're rotating around the y-axis, what you're going to do is, instead of drawing a vertical line, you're going to draw a line from the y-axis. So here's my dot from the y-axis, and I'm going to extend that all the way to my outer function there. So that's going to be my big R, and big R is that linear line, which is, I believe it was 1/3 x. So the linear line was y equals to 1/3 x. And then I'm going to draw another line, another dot right on the y-axis. Because I'm rotating on the y-axis, it makes sense to start at the y-axis. And then I will draw a horizontal line connecting to the inner function. And the inner function is basically this square root function, which was y equals to root x. Okay, so this is my little r, and this is my big R. Okay, so let's go ahead and set up the washer function. So v equals to pi onto the big R squared minus the little r squared times my height. Now, because I'm rotating around the y-axis now, my height is not dx, it's going to be dy. So let me erase that. So now I need a dy. And once you have a dy here, that literally means the functions on the inside, they have to be in terms of y. All right, you can't have x's in there, you have to have y's. All right, so that's a pretty simple fix. Let's do it. We know the big R is the root x function, and what we're gonna do there is, whoops. What we're gonna do here is we're gonna square both sides. And if I square both sides, I get x equals to y to the power 2. Okay, so this part right here, y to the power 2, that's the part that I'm going to insert for the big R. Okay, so let me just erase this and let me set up my next line here. So volume equals to pi bracket. So my big R is now going to be y squared, and that's going to be raised to the power of 2. Then minus my little r. Let me erase this now. Remember, little r was, oh no, actually I made a mistake here. My big R, okay, I'm gonna erase all of this. So I apologize, I did make a mistake there. Sorry, I didn't realize this. My big R is actually the linear function, and my little r is the square root function. Okay, so what I'll do is maybe I should just convert the equations right away. So if I have y equals to root x, and if I square both sides, that's going to be y squared equals to x. So let's box that. And then we also have this y equals to 1/3 x. And then I'm going to times both sides by 3. So that'll be 3y equals to x. All right, so these are my new updated equations here. And because my big R is the linear function, that means this 3y goes there, and this y squared would go there. So yeah, I'm sorry about that. I should have recognized that sooner, but after you start doing these video tutorials for so long, you start to go crazy and you lose your focus. Okay, so here we go. This is going to be 3y squared minus, it's going to be y squared, so that's going to be y squared, and that's going to be raised to the power 2 times dy, and volume equals to that. Okay, there you go. Let me erase all this now, and let's get into the actual math now. So this will be 9y squared, simplifying that, minus 2 times 2 is 4, so y to the power of 4. And let's go ahead and integrate this. Since we're integrating this with respect to y, we have to look at the y values, right? So if I just erase all this now, if you recall, this intersection point was 9, 3. So this is 3. So we're integrating all the way from the y values now. So I'm going from 0 all the way to 3. So we have to look at this vertically when we're integrating with respect to y. So we're starting at a low height of 0, and we go all the way to a max height of 3. So my boundary will be from 0 to 3. And that right there is my my volume equation there. Okay, so now I can finally take my antiderivative here. Sorry, this question is taking a little bit longer than I thought, so I do apologize for that. So let's go ahead and take the antiderivative there. So raise 2 by 1, which is 3, then divided by 3, minus, and that's going to be y to the power of 5 divided by 5, square brackets, and I'm going from all the way from 0 to 3, and then there's a pi in front, and volume equals to that. Okay, all right, so the 3 would go there and there, so that's going to be at 9 times 3 cubed divided by 3 minus 3 to the power of 5 divided by 5, and then if I put my lower bound to 0 there, that just gives me 0 overall, so I don't need to really focus on that. Yeah, I don't feel like doing the calculations here, but this is going to be 162 pi divided by 5 as your final answer for that particular problem. Okay, one more problem, and then we're done this homework video guide. Let's do one last question on finding the volume of the solid generated when we're integrating along the y-axis. Okay, so we have two equations here. So let's go ahead and graph those two equations. Actually, let me just a little bit more space over here. Okay, so I have this function here, y equals to negative x, which looks like that. And I also have this parabola here, which is 1/2 x squared, which looks like this. Actually, let me expand that a little bit more just to make sure I can get the full area there. Okay, so there's my parabola right there. And I'm rotating this around the y-axis there. Okay, just like all of these washer problems, I need to find the intersection points. Usually one of the intersection points that's given to me is the origin, which is 0, 0. And then let me go ahead and find that intersection point next. So in order to do that, I need to make the equations equal to each other. So that's going to be 1/2 x squared equals to negative x. And I'm going to bring the, I'm going to bring the negative x to the other side and make it positive. So positive x equals to 0. And then I can factor out the x's, and that gives me 1/2 x plus 1 equals to 0. And then this here is going to be x equals to 0. And this linear equation is going to be 1/2 x equals to negative 1. And that means x would equal to negative 2 if I times both sides of the equation by 2. Okay, and then if I go back to my diagram here, this right here is going to be negative 2. And let's go ahead and find the corresponding y height. That is going to be, well, if I plug in negative 2 there, negative 2 times negative 1 is going to be positive 2. Actually, let me just write this as a point, negative 2, 2. Okay, and then we're going to have this region right here. That's going to be rotated around the y-axis. And then a solid's going to be generated here. The solid's going to be very similar to some of the other solids that we've seen before. So I will probably not draw up some visual diagrams or show visual diagrams right away. Instead, let me go ahead and set up the washer equation here. So volume equals to pi times the outer function squared minus the inner function squared times the height. Now remember, since we're integrating along the y-axis, that means my height has to be dy. And then after that, let's go ahead and find our outer functions and our inner functions. Now in order to find our outer function, let me put a orange dot right here on the axis, on the y-axis, because that's where I'm rotating, and I will draw a line, and I'll keep on drawing it until I hit the outer function, which is the parabola. So the outer function is the parabola there. So I know the parabola has the equation y equals to 1/2 x squared. But since everything is in terms of dy, I need to write my parabola in terms of y. I have to make sure all these functions on the inside have the variable y. Okay, so I do have to make a little modification here. I can bring the 2 over there. So that'll be 2y equals to x squared. And then after that, I can take the square root of both sides. So square root that and square root that. So that means x equals to the square root of 2y. So this is going to be my outer function there. So let me just update that right away. So that's going to be pi times roots 2y and then the power of 2 there and then minus. Okay, and let's go ahead and find my inner function now. Let me just create some more space here. Let me just put a purple dot here right at the y-axis because I'm rotating along the y-axis. And with that purple dot, I'm going to draw a line until I get to my inner function, which is right there. And my inner function represents that blue linear line, which is y equals to negative x. All right, so in terms of writing this in terms of the other variable here, I can just take this minus sign and just transfer it to the y, so I have negative y equals to x. So that right there is my inner function, which represents that part right there. So if I complete this, let me put a bracket here in green. That'll be negative y, close the bracket, and then there's a power of 2 there because there's a 2 there. And then I'm going to multiply this by dy. Okay, after that, let's go ahead and set up an integral sign. And remember, we are looking at this in terms of y, so you need to focus on the vertical distance right here. So I'm going from a low height of 0, and I'm finishing with a height of 2. So I'm integrating all the way from 0 to 2. Okay, so before I take the antiderivative, let's go ahead and clean this up. If I square that, that's going to be 2y minus, and if I square that, that's going to be y squared. So 2y minus y squared in the brackets times dy, and I'm going from the integral from 0 to 2 with a pi in front, and volume equals to that. Okay, so now I'm actually ready to erase all this and start taking the antiderivative now. I might have to go from the bottom to the top here. So the antiderivative of 2y is going to be 2y squared divided by 2 minus, and then the antiderivative of y squared is going to be y cubed divided by 3. And then I'm going to put that all in a bracket, and then I'm going to go from 0 to 2 with the pi in front, and volume equals to that. Okay, let me just erase all this now. And we just change that back to proper 3. And now we can just insert our upper bound of 2 for my y's. And if I do that, I get 2 times 2 squared divided by 2 minus 2 cubed divided by 3. And the lower bound of 0 just kind of cancels out all the terms there, so I don't need to worry about that. Put that in a bracket, and then volume equals to all that times pi. And if you do the math here and work this all out, I believe you get 4 pi divided by 3 as a final answer there. Okay, so that pretty much concludes this video here. I do have a few more of these visual diagrams at the bottom if you're interested in seeing what the shape looks like, but that shape right there is being rotated around the y-axis. So you'll get another shape like that over here, and this is that region that was being rotated on the other side. And then here you can see we do have our washers being formed. And here's kind of a top view of that, and yeah, there's like a view from the top down again, where once again we're trying to find the outer function there, and we're also trying to find the inner function there. So I think that shape looked similar to some of the other problems that we had. But there you go, that's what that shape would look like, just for interest.